Welcome viewers to the second segment of the second lecture for the online series of lectures for the course of Algebraic Topology 2. In the previous segment, we stated the first theorem of this lecture concerning the zeroth homology group of a given simplicial complex. In this segment, we are going to start uh, with another version of this zeroth homology group um, using the notion of reduced homology groups. Okay, so let me get started with this definition first. Let epsilon be the map that we introduced earlier in the proof of the first theorem. It's a map from the group of zero chains on the complex K to the additive group of integers, which is the surjective homomorphism, surjective group homomorphism defined by, as we have defined earlier, its value on the elementary zero chain corresponding to the vertex V of the complex K is just 1. It's 1 for elementary zero chain V corresponding to a vertex V of the complex K. Okay. Then, if C is an arbitrary zero chain, epsilon of C, okay, since C belongs here, epsilon of C is here, and this equals the sum of the values of C on the vertices of K. Okay. Okay. Right. The map epsilon has a name. It's called an augmentation map. Augmentation map. Okay. For the group of zero chains on the complex K. We have seen in the proof of theorem 1 that the augmentation map on the on the on del 1 D, for where D is any one chain on K, is 0, right? For a given one chain D on K. This is what we have seen earlier during the proof of theorem 1. So we define the reduced homology group of the complex K in dimension 0, denoted by H0 of K with a tilde over, is equal to kernel of this augmentation map quotiented out by the subgroup of image of the boundary operator delta 1. This is our equation number 4. This is how we define the reduced homology group of the complex K in dimension 0. And what about the other dimensions? If P is strictly greater than 0, then we let the reduced homology group to be equal to the ordinary homology group. We let HP tilde of K to be equal to HP of K. Okay, so this is the definition of reduced homology group of a given simplicial complex. Now, the natural question that follows from is if we can connect the reduced homology group with the ordinary homology group of a given simplicial complex. And the answer to this this thing lies in the following theorem. So let me state the second theorem of this lecture, and then I'll prove it. Theorem 2, which sheds light on the relationship between these two homology groups, the reduced homology and the ordinary homology of a given simplicial complex in the 0th dimension. And in other dimensions, by the definition, they are the same. The group H0 tilde of K is free abelian. That's the first thing to see. And H0 tilde of K direct sum Z is isomorphic to H0 of K. All right. It follows from follows from the first theorem that if the underlying space of the complex K is connected, then there is only one component, and the 0th homology group of that complex is isomorphic to the additive group of integers. Okay. Thus, H0 tilde of K vanishes in this case, vanishes if the underlying space of K is connected. Right? If mod K is not connected, then this collection, okay, consists of one vertex. Then let this collection consists of one vertex from each component of K, as we have done in Theorem 1, from each component of the underlying space of the complex K. Okay, this is the first thing to do. We form this collection. Also let alpha sub 0 be a fixed index. Fixed index. We're not going to change it. Okay. From the index family, we choose a fixed index. Then the homology classes. Homology classes By the homology classes, I mean that I mean the 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 zero cycles that do not bound. Okay, the homology classes of the chains of the zero chains, to be more precise, V alpha minus V alpha 0, and we want alpha to be not equal to alpha 0, okay, so that it does not vanish. uh, this guy, this collection forms a basis for the reduced homology group of the simplicial complex K. Okay. Okay. So we pick up those zero cycles in this form that do not bound, and those zero cycles which don't bound form in this form. Uh, this collection forms the basis of this reduced homology group of the simplicial complex K. Okay. All right. So here goes the proof of the second theorem. Given a zero chain C on the complex K, we have seen earlier that C is homologous to a zero chain of the form C prime equal to sum of all these expressions n alpha v alpha, okay, sum over all alphas, and C prime bounds only if, by only if means this direction, only if C prime is equal to 0 or n alpha is equal to 0 for all alpha here in this expression. This is what we have seen during the proof of theorem 1. Okay. All right. Now, if C is in the kernel of this augmentation map epsilon that we have defined earlier before the statement of theorem 2, then from the definition of kernel, we know that epsilon of C is equal to 0. Now, since C and C prime are homologous, one has C prime to be equal to C plus a boundary term, right? Delta 1 D for some one chain D on K. D on K. So that one obtains epsilon of C prime is equal to, so from this expression, is equal to epsilon of C plus epsilon of del 1 D. Okay, and we can do this using the linearity of epsilon, since epsilon is a group homomorphism from the group of zero chains on K to the additive group of integers. And using this linearity property of group homomorphism, we can do it. Since Z is a group of integers, additive group of integers, right? That's why we have an addition here. All right. So now, since this guy vanishes, we have seen many times. We have mentioned it earlier, many times that uh, the augmentation map of such a boundary term is zero. Okay. Uh, so this is epsilon over epsilon of c. Um, so we see that therefore epsilon of c prime is equal to epsilon of c is equal to epsilon of c prime is according to this expression of linear combination can be written down as the sum of all these expressions n alpha v alpha, and we know that the value of epsilon on this elementary zero chains uh, are all one. So this is just sum over sum of all n alphas, and uh, since c is in the kernel of epsilon, this guy has to be zero. Okay, so this is we number this by equation number 5. So we get the sum of all the coefficients, the integral coefficients in this linear combination is 0. Okay, so this is an important equality. So let me erase everything. Now if the underlying space of K is connected, that is, it has one component, right? So and since it has one component, there is one n alpha involved in the analysis. There is one n alpha only. Then we have this expression sum of all the n alphas is equal to 0. So since there is only one n alpha, then we have n alpha is equal to 0. So that C prime, the zero chain with which C is homologous, okay, that zero chain C prime is equal to n alpha V alpha, and this guy 0, which implies that the kernel of epsilon is trivial, right? So an arbitrary element of kernel of epsilon is 0, which means that kernel of epsilon is trivial. By definition, the reduced homology group of the simplicial complex K is defined as kernel of epsilon quotiented out by modded out by image of delta 1, right? And kernel of epsilon is trivial. So this together with this implies that since image of delta 1 is a subgroup of kernel of epsilon, that has to be trivial as well, and hence the reduced homology group is 0. This is the case when the underlying space of the complex K has only one component. In other words, when this underlying space is connected. Okay, so now let this underlying space have more than one component. more than one component, let C belonging to kernel of the augmentation map as before, and remember this equation, sum of all the n alphas is equal to 0, which we numbered by 5, and this equation number 5 now yields, which was n sum of all the n alphas is equal to 0, where n alpha appears in this linear combination, right? N alpha V alpha, sum over all alphas, with C prime being homologous to C. Okay, given the fixed index alpha 0, C prime. So let us decompose this expression of C prime into two parts. C prime is equal to sum of all the expressions in alpha V alpha such that alpha is not equal to that fixed index alpha 0. Okay, so what we are left with is just n alpha 0 V alpha 0. We can always do that. This is our equation number 6. Okay. Now we know that sum of all the n alphas is equal to 0, which we numbered by 5, right? And this implies that, again we decompose into two parts, extract this alpha 0 part out of this sum, and we get minus sum of all the n alphas such that alpha is not equal to alpha 0 is equal to n sub alpha 0. That is our equation number 7. Now substituting 7 into 6, one obtains C prime is equal to sum of all the n alpha V alpha, where alpha is not equal to alpha 0, minus so from here, so we are substituting the value of n sub alpha 0 here in 6 using 7, and that gives me this expression. Alpha is not equal to alpha 0 times V sub alpha 0. Okay, and now so we can factor out this coefficient term, that being the same in both the summands, and which is n alpha, right? V alpha minus V sub alpha 0. This is equation number 8. This is how C prime looks in the case where the underlying space is not connected anymore. Okay, good. Therefore, C prime is a linear combination of the zero chains V alpha minus V sub alpha 0, V sub alpha 0. And as before such a zero chain C prime bounds if it is trivial. Okay, homology classes of the zero chains V alpha minus V sub alpha 0, where alpha is not equal to alpha 0. Okay, so okay, so let me erase this bottom part. Okay, so I want to mention something here. When I'm saying homology classes of the zero chains, I mean two chains, sorry, excuse me, two zero chains. So it's the homology classes that we are concerned with, which means that we are dealing with equivalence classes. So two zero chains. So we are picking up two zero chains from this class. Okay. So V alpha minus V sub alpha 0. This is one zero chain. And another zero chain is V alpha prime minus V sub alpha 0. So alpha 0 is a fixed index. We are not touching that. We're just changing alpha and remembering that alpha is never equal to alpha 0. Okay, so these two zero chains are taken to be equivalent. So since we are dealing with equivalence classes, there is an equivalence relation. What is that? They are taken to be equivalent, or they belong to the same equivalence class, to the same equivalence class, or we write it like this, right? V alpha minus V alpha 0 is equivalent to V alpha prime minus V alpha 0 if and only if V alpha minus V alpha 0 is equal to V alpha prime minus V alpha 0 plus delta 1 D. Okay, for some one chain D on this complex K. So this is what we mean by the homology classes of the zero chains here. Okay, it's a collection of equivalence classes, and these guys, since we have written down C prime as the linear combination of such expressions, right? And alpha times V alpha minus V alpha 0, right? And some they're summed over all alphas such that alpha is not equal to alpha 0. Okay, and that is precisely the reason these zero chains, this collection of zero chains, and also that no non-trivial zero chain bounds. Okay, so based on these 2 points, we figure out that these such classes of zero chains forms a basis of this reduced homology group H0 tilde of K. Okay, QED. So we are done proving the second theorem of this lecture. So now we come to the construction of a very useful tool called cone associated with a given simplicial complex. It is useful to determine the homology groups of a given n simplex. Okay? And we also see how we can compute the boundary of a given n the homology groups of the boundary of a given n simplex using this cone construction. Okay, So let me erase everything. The homology of a cone. The goal will now be to compute the homology group of an n-simplex and of its boundary, as we had stated earlier, and of its boundary. We therefore develop this very useful tool called cone. Okay. Okay, so let me give you the definition of a cone. Suppose that K is a complex in this space. This space has a name which is denoted by bold E raised to J, and it's called generalized Euclidean space. Okay, it's an infinite it's an infinite dimensional space. So I'm going to explain what it means by generalized Euclidean space very briefly in a minute. But before that, let me complete the definition. Suppose that K is a complex in e to the j, and W is a point of e to the j in this generalized Euclidean space, such that each ray emanating from W intersects the underlying space of the complex K in at most one point. It may not intersect, a ray may not intersect this topological space at all. There is no harm with that. But if it intersects, it at most intersects it at a point. That's the thing. Okay. All right. So before going, going further, we want to discuss very briefly this concept of generalized Euclidean space. You may not be familiar with this thing, but if you have studied product topology in the course of points topology, you may have been introduced to this notion of generalized Euclidean space there. At least you have seen this guy, r raised to any index family, j. J can be anything. It can be a continuous family, like r raised to this interval 0 comma 1. It can be something like this, or it can be r raised to r, or r raised to the set of rational numbers. Okay, something like this. J can be anything. All right, let J. So we are discussing generalized Euclidean space. Bold-faced E raised to J. Okay. So let J be an arbitrary index set Okay, and also let r raised to j denote the j-fold product of r with itself, j-fold product of r with itself. Okay, good. Like I said earlier, that it can be something like r uh, raised to the set of rational numbers, or r raised to r, or r raised to the set of natural numbers. Okay, so an element of this guy, this space r to the j, is treated as a function. An element here, an element is treated as a function from this set j to the set of real numbers. Real numbers r. Okay. Um, one usually uses tuple notation for an element r to the j. For an element here, one usually use this notation, x sub alpha, where alpha runs in the index family j. Okay, so an element is designated by by this symbol. Okay, the j-fold product of r with itself, uh, which uh, which we are denoting by r to the j, right? Um, so so before moving here, we are introducing this guy. Okay, so this j-fold product of r with itself, which we denote by r to the j, is of course a vector space with the usual component-wise addition and multiplication by scalars. Let me explain. Um, so it's a vector space. So we have addition of vectors. That's an element here in R to the J is denoted by X sub alpha, where alpha runs in the index family J. Suppose and so the two such elements are added in the obvious way. So this is addition in R to the j. Okay, and this is defined as x alpha plus y alpha sub alpha. This is addition in R. Okay, and how do you multiply a scalar k with an element here? It's also done in the most obvious way. K times x alpha. This is multiplication, scalar multiplication in the set of real numbers. Multiplication in R. Okay, and this multiplication is taken to be the multiplication in R to the j. Scalar multiplication in R to the j. Okay, so so one can check immediately that uh, with respect to these two operations, this guy R to the j forms a vector space. All right. Okay. Now let e to the bold-faced e raised to j denote the subset of R to the j. It's a subset of uh, the vector space R raised to j consisting of all points X alpha such that X alpha is a component of this J tuple, right? It's a J tuple, and X alpha is one component of this J tuple corresponding to alpha, the corresponding to the 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 index alpha. Okay, and X alpha is 0 such that X alpha is 0 for all but finitely many values of alpha. Finitely many values of alpha, which means that there can be there can be finitely many non-zero components in this J tuple. And if we take all such elements from R to the J, that is going to be a subset of R to the J, and we denote that subset by boldface E raised to J. Okay, so now let E sub alpha be the map from J to the set of real numbers where alpha is 1. Now, where um, its value, okay, its value for the index alpha is only 1, and otherwise it's 0. Okay, so since E sub alpha is a function from J to R, it only takes the value 1 on the index alpha, and it's 0 otherwise. Example, let me give you an example. Epsilon 2. This guy is a J tuple. This is a J tuple X sub alpha, where alpha runs in the index family J, such that, so this guy is a J tuple such that x2 is equal to 1 only, and here x alpha is equal to 0 if alpha is not equal to 2. Okay, this is what we mean by epsilon sub 2. All right, now I leave it as an exercise for you to check that this set epsilon alpha, where alpha runs in the index family J, is a basis for e to the j. Okay, remember e raised to j is a subset of, it's a proper subset of r raised to j, which consists of elements only, elements here whose who can only have um, finitely many non-zero components. Okay, all right. Okay, so you need to check that. It's left as an exercise for you to check that this guy is a basis of e raised to j, while you also have to check that e sub alpha, where alpha runs in the index family j, is not a basis for r raised to j. Okay, we call this vector space e raised to j the generalized Euclidean space. Okay, this guy is called the generalized Euclidean space, and we can put topology on this generalized Euclidean space introducing the following metric on it. So x, so we denote this element of e to the j by x, okay, and so there is another element y of e raised to j, okay, and the distance between these two elements is given by max. So it instead of sup, it's a max because of e to the j. Okay. Where alpha runs in the index family j. Okay, so with the help of this metric, we can put topology on this generalized Euclidean space, and hence it becomes a topological space. Okay, and this topological space is coined as generalized Euclidean space. Okay, everything we have done so far for complexes in R to the n, where so we have done complexes in R to the n, where n is a natural number, right? Whatever we have done for complexes in R to the n also applies to complexes in this generalized Euclidean space. Okay, so back to the definition of cone. Back to the definition of cone. It's time to give you some examples of cone. Okay. Let me take K to be a one-dimensional complex in R2. Okay, let K be this one-dimensional complex in R2, and W be this point inside this one-dimensional complex. So K is a one-dimensional complex in R2 in the Euclidean space in 2 dimensions. Okay, and right, and so let me number this figure as figure 2. It's a 1D complex K in R2, and W is a point in the 2-dimensional Euclidean space such that each ray emanating from W intersects the underlying space, intersects the underlying space in at most one point, right? So whatever ray I try to draw from W, it will intersect the the given one-dimensional complex in at most one point, right? Like this. So this is what we have mentioned in the beginning of the definition. Okay, so let me give you another example. This time we have a two-dimensional complex in three-dimensional Euclidean space. Let me draw it. So it's in the form of uh, uh, a hexagon. like this. So this is the two-dimensional region. It's a two-simplex, right? Then we have another two-simplex here. This is another two-simplex. And this is a two-simplex here. So we have four two-simplexes altogether. Four two-simplexes altogether. And this is the complex K. It's a 2D complex. And W is here. W is a point in R3, right? So you can immediately see that if you draw a ray from W that may not intersect K, there is no harm with that. But if it intersects K, it is going to intersect it at most one point. Okay, so it does not intersect K in more than one points. Okay, so in this figure, which is figure 3, we have drawn a two-dimensional complex K in R3, and W is a point in R3 such that each ray emanating from W intersects the underlying space of K in at most one point. Okay. Now it's time to, so if these properties hold for the given point W and the given simplicial complex K in the generalized Euclidean space e to the j, we define the cone on K, the given simplicial complex, with vertex of that cone being the point W, with vertex W to be the collection. It's a collection of simplices to be the collection of all simplices of the form W comma A0 all the way up to AP, where A0 all the way up to AP is a simplex of K. Okay. So this is a P simplex of K, and we are forming P plus 1 simplices, right? Where it's a simplex of K along with all faces of such simplices. Okay, so what's the collection? It's the collection of all simplices of this form and all the faces of such simplices. Okay, so if we take all of these simplices and their faces together, the collection is called the cone on K. We denote this collection. We denote this collection by W star K. Okay, so it's time to give you the example. So we have drawn earlier the two-dimensional complex in R3, right? So this was in figure 3. Remember, in figure 3 we drew this two-dimensional complex K, and the point W was situated here, right? Now so for example, we can pick up this two simplex of this complex K, and and with the help of this point, we can form three simplex, all right, like this, which is a tet tetrahedron. Okay. Similarly, you can do you know, uh, you can form other simplices. So, for example, this is another tetrahedron. We can get, if we take the base to be this two simplex of the given simplicial complex K. Okay. So this figure 4 tells us how to form the cone W star K, which is a 3D complex in R3. Okay. It's a, it's a, it's so we have a region, a three-dimensional region bounded by a surface that is going to be the cone W star K, a 3D complex in R3 with K being the 2D complex in R3 given in figure 3. Okay. So I leave it as an exercise for you to show rigorously that W star K is a well-defined complex. Okay. And and it contains, so the complex that you get here is it has K to be a subcomplex inside W star K. Okay, K is called the base of the cone. So K has a name. K is called the base of the cone. Okay, all right. So I think it's a good time to take a break. Okay, so I'll come back in the third segment with more examples of cone. Okay, and then we'll try to see how we can compute the homology groups of of cone. Thank you for attending this second segment.